Hi class, today we are going to learn about the cosine law. So it's a new law to be used with acute triangles when you can't use the sine law. So remember, to use the sine law, you need a known ratio. So that's a known angle and a known side that are across from each other. But we don't always have that. So the sine law actually allows us to solve for triangles that don't have that. So that's really handy. So this is a bit different because I'm actually going to be developing the formula for you guys instead of just, sorry, I'm just playing around with this bit because I was having some trouble. I'm actually going to be developing the formula for you. So I'm going to just explain a bit about the formulation of this triangle or of this law. So notice that this is an acute triangle that's been divided into two right triangles, okay? Side C is across from angle C, side B is across from angle B. Now we have labeled side A across from angle A, but notice that we've broken it up into two sections, okay? So this right triangle and this right triangle. So we've labeled this one X, and if this is X, then this has to be A minus X, because together they add up to A. All right, so this X just refers to here to here, and the A minus X is here to here, whereas A is the entire side. Okay, so let me first tell you what the cosine law is, and then we'll go back up and I will show you where it came from. So we can write the cosine law, there's three different ways to write it. One is A squared, so that's the side length A, equals B squared plus C squared minus 2 BC cos A, big A. Okay, notice here that the side length that's on this side of the equal sign is the same as the angle that's on this side. Okay, so if it's the B that's unknown, you can write it as B squared equals A squared plus C squared minus 2AC cos B. So notice also that whatever two letters are here and here are the same two letters that are here and here. And those are the letters that are not the one that's on the other side of the equal sign. Finally, if you're trying to solve for C, you have C squared equals B squared plus A squared, or I could have done A squared plus B squared, minus 2AB cos of angle C. Okay, so what this tells us is to find the length of a side. You take the squares of the other two sides, subtract 2 times the sides, and times it by the cos of the opposite angle. So we'll obviously be doing some examples of this. So that looks like a pretty fancy formula. Where on earth did it come from? Okay, so this part, you know, is a little bit advanced, but as academic students, we care about where formulas came from, okay? We don't want to just accept everything at face value all the time. So basically, I'm going to start by setting up 3 equations that we know are true, and I'm going to substitute 2 of the equations into the third one, or in this case, the first one, and solve for the unknown. So we're just going to use SOHCAHTOA and Pythagorean theorem to write some known equations. Okay, so the first thing that we know is if we look at this triangle here. Which one do I want to look at? This one here. Okay, so this right triangle. So from here to here. Sorry, I'm having big troubles with my pen. So that's the triangle I'm looking at, but I'm going to erase that just so we can still see the labels. Okay, so I'm looking at this triangle here. If we use Pythagorean theorem, we can see that B squared is equal to H squared plus, in brackets, A minus X all squared. Okay, so you can just put on the side, that's Pythagorean theorem. That's where that came from. So if we expand this, and collect like terms, what you'll get is that B squared equals h squared plus a squared minus 2ax plus x squared. Okay, that's what happens when you expand this. So I'm going to put a big box around that and call it equation number 1. Sorry about my software problems here. Hopefully it's not too much of a problem. Okay, so that is equation number 1. Okay, now we're going to come up with equation number 2. So equation number 2 uses SOHCAHTOA in this bigger right triangle. Okay, this one from A to B, this right triangle. So we're just going to write that we know that the cos of B is equal to adjacent, so that's x, divided by hypotenuse, hypotenuse, so that's c. So cos of B is x over c. So we can arrange this, that x is equal to c times cos of B. Okay, so that is our next equation, and we're going to call that equation 2. Oh, this is funny. Okay. Doing my best, guys, doing my best. Okay, one more equation we're going to come up with, and that is Pythagorean theorem from this bigger triangle. So from here, we can see that h squared, actually I'll write it over here, h squared plus x squared equals c squared. So we can rearrange this to say h squared equals c squared minus x squared. Okay, and that is equation 3. Okay, so all 3 of these are just equations that we came up with using this well-labeled diagram and using Pythagorean theorem in the case of the red and the blue, and just using SOHCAHTOA, so the fact that cos of B is adjacent over hypotenuse, to come up with these 3 things. So these are all just equations we've made based on what we already know. So what we're going to do now is like a good trick to use in mathematical proofs. We're going to sub the information from equation 2 and from equation 3 into equation 1. Okay, and when we do that, we're going to be able to simplify it, and we're going to get the cosine law from before. So equation 1 was b squared equals, so I'm going to leave it as b squared. Now notice, instead of this h squared, I'm going to put the blue equation in instead. Okay, sorry, I'm just having some trouble here. So instead of writing h squared, I'm going to write c squared minus x squared in for h. So that's from the blue formula. So c squared minus x squared. Okay, and then it says plus a squared. So I'll put plus a squared minus 2ax plus x squared. Okay, so all I've done so far is put number 3 in. So what do you notice here? Well, look at, we have a minus x squared and a plus x squared. So those cancel each other out, which is pretty handy. Okay. Oh my word. There we go. Okay. Those two cancel each other out. Okay, so now we're left with b squared equals c squared plus a squared minus 2ax. Okay, so now what I'm going to do is, instead of x, okay, I'm going to write the green equation, so c cos b. So now what I get is, where's my pen? I'm almost there. Okay, b squared equals c squared plus a squared minus 2 bracket c cos b. And there you have it. So this is actually already the sine law. So this tells us that if we have an unknown side length b, okay, but we know the other two side lengths, so we know side length C and A, and we know how long B is, or how big the angle B is, we can actually solve. Okay, there should be an A here. Okay, so basically the understanding that you need here is that the development of the cosine law came from some known Pythagorean theorem formulas and a SOHCAHTOA formula, and just subbed these two equations into the other and rearranged to find the cosine law. Okay, so you need to have this cosine law memorized, and now we're going to go through and actually do some examples of how to use it properly. Okay, so all of these examples actually require us to draw the triangle, so you need to be good at knowing how to label triangles properly with the side lengths with the same letter across from the angles that have the same letter. So I'm going to just draw a generic right angle triangle. Remember, it doesn't have to look accurate at all. Okay, you just need to make sure that you're labeling across from each other as you need to. So we'll call this D, E, and F. Okay, and I'll label it with blue here. So we know that D is 4.9, so that's across from there. So this is 4.9. Okay, F is 6.2, so across from here is 6.2. And angle E is 64 degrees, so that's in here. We have 64 degrees. Okay, solve this triangle rounding measures to the nearest tenth of a degree. So notice that we're not able to use SOHCAHTOA because this is not a right triangle, and we're not able to use the sine law because we don't have a known ratio of an opposite side length to angle. So we need to use the cosine law, and we're going to first use it to find side length E. So in this case, E squared would be equal to the other two side lengths, so F squared plus D squared minus 2FD cos E. So the big key here is that whatever big letter you have here has to be the same as the little letter over here. So now we can fill in what we know. So this is equal to 6.2 squared plus 4.9 squared minus 2 times 6.2 times 4.9 times cos of 64 degrees. Now the nice thing is that your calculator can do all this for you as long as you're entering it properly. So I encourage you to try that now. You should get that E squared is equal to 35.815. Okay, so we're not done yet. That is what E squared is equal to. So now we need to solve for E by just taking the square root, and you get 5.985, which rounds to approximately 6.0 centimeters. So notice that I'm writing it as 6.0 centimeters and not just 6. And that's because both of these side lengths are written to the nearest tenth. So I want to make sure that this side length is written to the nearest tenth. Okay, so now I know this is equal to 6.0. Okay, so now I need to solve the triangle, so I need to find the other two angles. All right, so now I can actually use the sine law because now I do have a known ratio from here to here, so I can use the sine law. So in this case, I'm going to solve for angle F first. You don't have to. You could have solved for angle D first, but I just did angle F, okay? Okay, so we have that sine of F divided by 6.2 is equal to sine 64 degrees divided by 6.0. Okay, And I'm not going to do a whole note on the sine law again. If you don't know how to solve for this, you can go back and watch the sine law note, but you should get that angle F is 68 degrees. Okay, and then after that, you can just use the fact that they all add up to 180 to find angle D. So angle D is going to be 180 degrees minus 64 degrees minus 68 degrees. So angle D is equal to 48 degrees. Okay, so now I've solved the triangle. So notice that the cosine law is the most difficult law. It's a lot longer than the sine law. So we do try to use the sine law if we can because it's simpler. So in this case, I could have used the cosine law to solve for an unknown angle, but I used the sine law instead because it's simpler. All right. So here we have an acute triangle. So now they're not asking us to solve the whole thing, thank goodness, just for one side. So again, you just draw a basic triangle, label one P, R, Q. Okay, and then you just need to make sure you're labeling the appropriate side. So across from P is 5.9, which I cannot see my marker at all. Where am I? Okay, and across from R is 2.3. Okay, and across from Q is 6.2. Okay, so how do we find angle P? Well, angle P is here, and across from angle P is 5.9, which is here. So I need to be able to set up an equation where I get angle P at the end. So I want cos P at the very end. So that means I need to start with something that equals P on the outside, because remember that whatever angle is out here is the same as whatever side length is at the beginning. So I want to start with P squared equals, and then I have my other two variables. So R squared plus Q squared minus 2RQ cos P. So now you just need to sub in what you know, okay, and solve for P. Okay, so eventually you're going to have to be able to undo your cosine ratio to solve for P, because all of these sides are known, so the only unknown will be P. Okay, so you get 5.9 squared equals R, so 2.3 plus 6.2 squared minus 2 times 2.3 times 6.2 times cos P. Okay, so when you actually go and solve for this, you just need to, again, be very careful with your calculator work. Okay, so you're going to get minus 8.92 equals negative 28.52 cos P. So when you rearrange, you divide both sides, you get cos of P is equal to 0.31276. So to solve for angle P, you do the inverse cos, so cos to the negative 1 of 0.31276, and you get 71, actually it rounds to 72 degrees. Okay, so just to go through what you need to do on your calculator, because I do want you to get out your calculator and make sure you can do this. So how did I get this minus 8.92? Well, I just did 5.9 squared, and then I moved the 2.3 squared and the 6.2 squared over. So 5.9 squared minus 2.3 squared minus 6.2 squared gives me this number. And this negative 28.52, that would just be the negative 2 times 2.3 times 6.2. That's that number. So getting those separate is ideally what you would like to do. Okay, so I'm actually going to stop this video now just because I seem to be having some trouble with the software, and I'm going to record example 3 and 4 in a separate video. Hopefully I can fix my bugs here. So thanks for watching the beginning of the video. I hope you learned lots, and if not, I hope you learned even more in example 3 and 4.